So far, we have looked at how we can find delta H experimentally using calorimetry, or inferentially, meaning we're inferring what it is, using Hess's law, and that's what we just did in the previous two examples. Another way to calculate the heat of reaction is using tabulated standard enthalpies of formation. Now, delta H is the change in energy, and so we can define zero to be something convenient. Much like with changes in altitude, we have defined zero to be sea level. Why isn't zero altitude the center of the Earth? It's a little hard to measure from the center of the Earth, especially many, many, many years ago when we didn't know how big the Earth was, right? But sea level is just right there where you can see it. So we picked sea level to be zero altitude. So we're going to measure changes in enthalpy relative to the enthalpies of pure elements in their standard states. So we're saying, well, elements in their standard states, like the building blocks, and we'll call that zero, and whatever happens in combining those, whether it's positive or negative, that'll be the change. So we have to talk about what are those standard states. So the standard state of a material is a defined set of conditions. So if we're talking about a gas, it'll be the pure gas at 1 atmosphere of pressure. If we're talking about a liquid or a solid, it will be the pure liquid or solid in its most stable form. Mostly there's only one form, but some of them have more than one form. At 1 atmosphere of pressure and the temperature of interest. So this is not STP, although standard pressure is 1 atmosphere. Usually this occurs at 25 degrees Celsius, which is considered room temperature. It's 22.6 in here, so I think that's a little warm for a room, but that's what everybody says. If you have a solution, something dissolved in a liquid, then the standard state is the solution with a concentration of 1 mole per liter. What we're calculating here is called the standard enthalpy change. So we've got the delta H now with this degree symbol up here, which is indicating that everything's in their standard state. So we were going to do this based on standard enthalpies of formation. So now we've added an F subscript, delta H 0F. Standard enthalpy of formation. That is the enthalpy change when you make 1 mole of that compound from the elements in their standard states. It's also called standard heat of formation. The elements have to be in their standard states. For a pure element in its standard state, delta HF is 0 because we defined it that way. The enthalpy changes are measured relative to elements in their standard states, just like we measure altitude relative to sea level. So this is a table 7.5 from the textbook, showing standard enthalpies of formation for several different things. So here's bromine. So bromine is an element, but it could be Br or Br2. Well, if we were just thinking about it and looking at the periodic table with what we have learned, would we expect bromine to be found as Br2 or Br? 7 diatomic elements. Horses need oats for clear brown eyes. Bromine is a diatomic element, right? So we've been using it as Br2, and that is its most stable state. So Br2 is the standard state for bromine, and it's a liquid at room temperature, which we can tell from the color of its symbol on the periodic table. That's going to have a heat of formation of 0. If we make bromine atoms in the gas state, that's going to require you to put in 111.9 kilojoules for every mole of bromine that you do that to. Some elements, like carbon's not diatomic, still has more than one form. There's graphite and diamond. How do we know which one is the standard state? Well, it's the one with a 0 heat of formation. So the standard enthalpy of formation for methane, that was under carbon, right here, forming CH4 is negative 74.6. So the heat of, isn't that weird? That, I don't know what it's doing. That was weird. I have that recorded so I can go back and look at that. Forming 1 mole of methane from the elements in their standard states. So we can write an equation describing how that's formed. So this is called a formation reaction, and we're always making 1 mole of this compound because the delta H is in kilojoules per mole. So we want the delta H to match up to this equation. In order to have 1 mole of product, we sometimes have to have fractions on the other coefficients. I already said that. So let's look at the formation of carbon monoxide. So carbon monoxide in the gas state, we're trying to write the equation describing that its formation from elements in their standard states. So we see that in carbon monoxide there's 2 elements, carbon and oxygen. We've got carbon and oxygen. But we have to identify their standard states. So the standard state for solid carbon is graphite. So we have to specify that. And the standard state for oxygen is O2, gas, because it's a diatomic element and it's a gas at room temperature, right? This equation is not balanced. Normally, in all the other things we've been doing, we would balance this by putting a 2 over here and a 2 over there. Ta-da! Done. But then we end up with 2 moles of carbon monoxide and we only want 1. So we have to only adjust the reactant coefficients. So we can do that by putting a fraction in here, 1/2. If you think of this in terms of atoms and molecules, 1 atom of carbon, 1/2 a molecule of oxygen. Wait, you can't. Then it's not the same, right? But we're not really talking about individual atoms and molecules. We're talking about moles of molecules. So can you have 1/2 of a mole of oxygen molecules? Yes, you can. So normally we don't have fractions in balanced chemical equations. But when we write these formation reactions, sometimes they're necessary. And then we can look up delta H, heat of formation, for that in that table. And there it is. Any questions? Let's practice. Write equations for the formation of sodium chloride solid and lead to nitrate solid from the elements in their standard states. Include the values of heat of formation for each equation. Well, let's do the first one first. So I want to write a chemical equation showing how 1 mole of sodium chloride forms. So I have to look at my product formula and identify what elements are in there. I've got sodium and I've got chlorine. And then we need the standard states. You can always go to the table and look those up, but most of these you can also just get from the periodic table with a little bit of common sense. Sodium is a metal, right? Is it a diatomic element? No, none of the metals are. So it's just Na. And what does its state at room temperature? It's a solid, because its letters on the periodic table are black, and all the black ones are solids. Chlorine. Is chlorine diatomic?
Yes.
Yes. That's the clear in the clear brown eyes. So Cl2, what's the state of chlorine at room temperature? It's a gas. Because it's red up there. Okay, so those are my elements in their standard states. I need to balance this equation without putting any numbers over here. So there's one sodium and one sodium, but here they come in pairs, and here there's only one. So I need 1/2 of that. Okay? And then I'm supposed to include the heat of formation. So I find that by looking it up. So we go back to this table. Here's sodium. Here's sodium chloride, solid, negative 411.2 kilojoules per mole. Negative 411.2 kilojoules, because this is written for 1 mole. Let's do the next one. So a PbNO3 2 solid. This one has more elements. It has lead, and it has nitrogen, and it has oxygen. Is lead diatomic? No. What's its state at room temperature? It's a solid. Okay, so there's that one. Is nitrogen diatomic? Yes, it is. And what is its state? It's a gas. You know, it's in the air we're breathing right now. Is oxygen diatomic?
Yes.
Yep. And it's a gas. So the elements written in their standard states. If you're not sure, you can go look it up in the table. Now I need to balance the equation. So there's one lead here and one lead over there. So far, so good. How many nitrogens are in one of this?
2.
There's 2 of them. Oh, cool. We've got 2 over there. And how many oxygens are over here? 6. So how can I make this into 6? I'm going to multiply by 3. And leave a little room here. So the heat of formation for this one, you can't find in that table. You have to go to the back of the book. So this is excerpts from an appendix in the back of the book. It gives a lot more compounds and elements. But there's 3 columns of numbers. The first one is the heat of formation. That's what we're interested in. This is Gibbs free energy, and this is entropy, and you're not going to need those until you take Chem 1B. So we're looking for lead 2 nitrate. So lead is over here, and there it is, PbNO32S. So minus 451.9. Kilojoules. Okay? So now we're going to kind of start putting together, why did we learn all these things just now? So the heat of formation represents or corresponds to the formation of a compound from its elements in their standard states, right? So we're starting with elements, we're making a compound. That's the heat of formation. What if we reverse that, and instead of forming the compound, we decompose it into its elements? When you reverse the reaction, what do you do to delta H? You change the sign. So compound being broken down into its elements would correspond with negative heat of formation. So this is where it gets simpler and we don't have to add a whole bunch of chemical equations together. We can think of this as we're taking the reactants and we're decomposing them into their elements, which is 0, and then the products we're assembling out of those. And so we're going to have negative heats of formation for the reactants and positive ones for the products, and we're just going to add them all up, basically. Because any reaction can be written as the sum of the formation reaction, or the reverse of them. So the way we usually talk about this is the standard heat of reaction. We are going to take the heats of formation of all the products. If there's 2 moles, then we multiply by 2. Whatever the coefficient is, we multiply by, because more stuff, more energy. So those are all positive, and then we're going to subtract the heats of formation of the reactants. We could add the negative, but this is the way they always show it. And when we see this Greek letter delta, that means final minus initial. So we're taking the heats of formation of the final things, the products, and we're subtracting the heats of formation for the initial things, the reactants. So this is how it's written mathematically. That capital sigma means the sum of, and n here represents the coefficients for the products, and this is the coefficients for the reactants. So here we can look at this in different ways. So this is the overall reaction that we're looking at. Methane plus oxygen to form CO2 and H2O, combustion of natural gas. So we could take these 3 chemical equations and rearrange them and combine them to get this. Right? So this one we'd need to do in reverse, and that one's okay, but this one would need to be multiplied by 2. Right, and then we do those things to this, and we'd add them all up, right? Or we can think of it this way, okay, starting with our reactants, methane and oxygen. We're going to decompose them into their elements. So carbon and 2 H2s. The oxygen was already an element in its standard state. And then we're going to make one of the products, the CO2, and then we're going to make the other product, 2 moles of water. And so we've got these 3 steps, and they add up to this number. But learning this equation here, we can do it without writing chemical equations and messing around with all of that stuff. Let's do that again. I couldn't make it do that if I wanted it to. So the way we're going to calculate using heats of formation, we're going to say the standard heat of reaction. We're going to look at the products. So here's a product, CO2. There's 1 mole of it. So I have 1 mole of CO2, and the heat of formation for CO2 is negative 393.5 kilojoules per mole. I'm adding up for all the products. So there's carbon dioxide, and then I've got 2 moles of water. So 2 moles times the heat of formation of water, negative 241.8. kilojoules per mole. There's parentheses and a big bracket there. Sure, if you say so. So these units cancel, don't they? That's the final. Those are the products. I'm going to subtract a similar sum for the reactants. I have 1 mole of methane, and I'm going to use the heat of formation for methane, minus 74.6 kilojoules per mole. Those moles cancel out. And then the heat of formation for 2 moles of oxygen. Except oxygen is an element in its standard state, so its heat of formation is 0 kilojoules per mole. So I have negative 393.5 plus 2 times negative 241.8 minus the quantity, negative 74.6 plus, 2 times 0, close parentheses. So 2.5 kilojoules. I can look up the heats of formation and just look at this equation. 1 times the heat of formation of this plus 2 times the heat of formation of that. Subtract 1 times the heat of formation of this and 2 times the heat of formation of that. And I can get my delta H without writing equations and rearranging them. I can do this because if I take these formation equations, I can combine them to get this. Two examples and then we're done. The thermite reaction in which powdered aluminum reacts with iron oxide is highly exothermic. Use standard enthalpies of formation to find the standard heat of reaction for the thermite reaction. So what I need to do is I need to look at all my products and reactants and I need to find their heats of formation. Are any of these elements? Yeah. Aluminum, solid. Aluminum's not diatomic, it's solid at room temperature. So its heat of formation is 0. That's an element in its standard state. What about Fe solid? Also an element in its standard state, so that one's 0. I need these two guys. So I'm going to go and look them up. So over here, there's my Al2O3, and that's negative 1675.7. And then I'm also going to need the iron one, which is Fe2O3, solid, negative 824.2. So this is negative 824.2 kilojoules, and this guy's negative 1675.7 kilojoules. We're going to take the product heats of formation and subtract the reactant heats of formation. So the standard heat of this reaction is going to equal the products. So here I have aluminum, and there's only one, right? So I've got 1 times negative 1675.7 plus 2 times 0, if you want to be specific. and I'm going to subtract the reactants. Well, aluminum, there's 2 of them, 2 times 0. And for the iron, there's only 1, and it's negative 824.2. So I've got negative 1675.7 minus negative 824.2. What did I do wrong? Oh. So this is negative 851.5. This represents taking all the formation reactions and manipulating them and adding their heats of formation together. And this is the last one. Back to those chemical hand warmers. They produce heat when they're removed from their airtight plastic wrappers. I talked about why that is. Iron is going to be reacting with oxygen from the air, and essentially it's rusting. It's forming Fe2O3. Calculate the standard heat of reaction for this reaction, and calculate how much heat is produced from a hand warmer containing 15 grams of iron powder. Well, let's do the first one first. Calculate delta H. We need to find the heats of formation, standard heats of formation for all the reactants and products. Well, look, the reactants are both elements in their standard states. So those are both 0. And then we need to look this one up, except we just used that one in the previous example. That's negative 1675.7. No, it isn't. That was the aluminum. It's 824.2. So to calculate the standard heat of reaction, I'm going to take my products, 2 moles of Fe2O3, so 2 times the heat of formation, and that's the only one. And then I'm going to subtract 4 times 0 and 3 times 0. Could you skip that part? Of course you could. Negative 1648.4. So the standard heat of reaction for this is negative 1648.4 kilojoules. I was saying, how much heat if 15 grams of iron reacts? So that's thermostoichiometry, I guess you could call it. So with stoichiometry, we're always just going to start from grams to moles to grams, and make changes as needed. Are we starting with grams? Yes. We're starting with grams of iron, so we can go to moles of iron. Am I trying to find out a mass? No. I'm trying to find out how much heat. Well, this is kilojoules per mole, per 4 moles of that, or 3 moles of this, or 2 moles of that. I don't need to do another mole thing in here. And I'm not going to grams, so I can go straight to kilojoules. So I'm going to have 15.0 grams of iron. I'm going to convert that to moles of iron, and then I'm going to convert that to kilojoules. I'm going to divide by grams of iron, so the units cancel. I'm going to divide by moles of iron, so the units cancel. This first term is the molar mass of iron. 1 mole of iron is 55.85 grams. And this comes from delta H. It's this many kilojoules, negative 1648.4, for how many moles of iron? For 4. 15 divided by 55.85 times negative 1648.4. I often forget. Don't forget to divide by 4. And then I get negative 110.68. I should have 3 sig figs. So we're going to call that minus 111 kilojoules. If this was a mastering chemistry question and you typed in as the answer to how much heat is produced, negative 111 kilojoules, would say you're wrong. If I ask you how much you paid for your shoes, are you going to tell me you paid negative $100? No, because that would imply that the store paid you to take the shoes. If so, I really want to know where that store is, because I need some shoes. Right? Why don't we say the negative? Because if we're talking about you and you paid for the shoes, we understand that the money left you. We don't need a sign on it. The words here, how much heat is produced, it's not how much heat is absorbed, how much heat is produced, how much heat is given off. And so an answer in sentence form would be 111 kilojoules of heat is produced. It's not really a sentence, but in words. Any questions? I will not try to trick you with negative signs like that on an exam. But if you're doing homework or worksheet problems and you come up with something weird like that, it's probably the words.